I'm Dominik Koller, and I'm currently a PhD at Petra Ritter's brain simulation section. And we are going to explore cortical traveling waves today and try to understand their underlying principles. Okay, first of all, let's see. Okay, so first of all, we're gonna have a look at what traveling waves are, where they are, what their function is, and what could possibly go wrong in a clinical setting. And in the second part, we will have a look at mechanisms, how to model traveling waves, and in the last part, I will tell you a little bit about my current research in which I'm trying to understand how the structural connectivity guides traveling waves. If you search for brainwaves on Wikipedia, you get to the disambiguation website, and if you follow the link to brainwaves, you end up on the page for neural oscillations. And it says in the first sentence that neural oscillations or brainwaves are rhythmic or repetitive patterns of neural activity. Now, as you can already see, this hints at the fact that traditionally neuroscience has viewed these classic brain rhythms as oscillations. However, more recent evidence has sort of rectified this term in the sense that it started to show that all of these classical brain waves are actually traveling waves, and therefore has sort of shown the real nature of brain waves. And to understand the subject a little bit better, let's first talk about what are traveling waves in general. So traveling waves are basically, I guess the most intuitive way to explain them are ocean water waves that you can see here in the background, and they travel from offshore to the beach. And more specifically, the definition of a traveling wave would be a disturbance in space and time that is organized regularly. So in this illustration here, you can see an illustration of such a wave, and you have a space and a time axis, and the wave is propagating through time and has this shape in space. And waves can usually be classified or characterized by a couple of properties. One of them would be the amplitude, which is the magnitude of the disturbance. And another one would be the wavelength, which is related to the spatial frequency of these waves. One further property would be the temporal frequency, which if you look at, for example, one point, how often does the wave cross this point in a certain time period? And lastly, you would have the wave velocity, which describes the direction of the wave and its speed. Now, the disturbance doesn't necessarily have to be the water level or the vertical position of water molecules, as it is the case in ocean surface waves, but it could also be, for example, as you see here, a disturbance in the color of, in this case, chemical solutions. And this is the so-called Belousov-Jabotinsky reaction. It's a mixture of chemicals, and under certain conditions, they start producing traveling waves in the Petri dish, as you can see here, and which I find is a very beautiful reaction. So there are also chemical waves. And now let's jump to neural traveling waves. And here you see one example of such traveling waves, and in this case the disturbance is in the voltage amplitude across a microelectrode array that was implanted in the visual area MT of marmoset monkey. And as you can see, this microelectrode array is on the order of a few millimeters, so this wave would be an example of a small scale wave. And the wave speed has been estimated at around 0.1 to 0.6 meters per second, which suggests that the fiber network underlying these traveling waves could be unmyelinated axons. All right, and what we see here is a set of voltage fluctuation. In this example, you see a 3D reconstruction of an epileptic patient's brain. So sometimes if epilepsy cannot be treated with medication, these people have the option to undergo surgery to basically remove the epileptogenic tissue. And to do so, doctors usually implant an ECOG area, which are the circles that you see projected on top of this brain. They implant such an ECOG area underneath the skull and on top of the cortex. So this has a very good signal to noise ratio. And the purpose of doing this implant is to detect over multiple days where the epileptic seizure originates from. Such that once the tissue is located, it can be resected. And in this study, we looked at cortical traveling waves in sleeping patients. And as you can see here, the activity propagates in a rotating wave around the center of this ECOG area. And this would, of course, be an example of a large-scale traveling wave that spans almost across the entire cortex. And as you can also see on the slide, the wave speed of this rotating wave has been estimated at about 2 to 5 meters per second, which is much faster than the example that we saw before. And this suggests that the underlying fiber network that produces this traveling wave is actually myelinated axons of the white matter fiber tracts. And here in a last example, we see actual bold fMRI traveling waves, and they have been found to be time-locked to arousal fluctuations. And as you can see, in this study, they actually found these waves in the cerebral cortex, striatum, thalamus, and the cerebellum. And the authors actually hypothesized that these traveling waves are the basis for the classic functional connectivity networks that we observe in fMRI research. Again, this would be a large-scale traveling wave, and also on a much slower frequency scale. So these are so-called infraslow bold fMRI waves that are below 1 Hertz. Okay, so if traveling waves are so ubiquitous, why have we not paid more attention to them? And I think the reason for this is that they are notoriously difficult to detect, because typically they vary a little bit, and so you have to look at single trial level traveling waves. And as you might know, traditionally neuroscience has had a problem with single trials because of the contamination with noise. And to ameliorate this issue, usually what we did is we trial averaged. So we took the average across all single trials to identify a common activity. So here in this example, you see the recording sensors have been ordered spatially, and you see the activity in time is tilted here, which is usually indicative of cortical traveling waves or traveling waves in general. And if you have multiple such trials and you add them together to get the trial average, you end up with a picture like this. So as you see, in each single trial, you would observe traveling wave behavior, but in the average, you maybe see a bump that is common to all of these single trials. So with more recent advances in technology and analysis techniques, we have sort of solved this issue, or maybe not completely solved, but we ameliorated this issue. So nowadays we're better capable of detecting such waves and analyzing them. But first, I'll introduce you to a couple of different studies that have investigated the function of traveling waves. In this first study by Davis and Lyle Muller and authors, they have found that traveling waves actually modulate the neural responses and also gate visual perception. So in this study, they trained monkeys to first focus on the center of a screen, then they would hold the fixation, and after a random duration of time, the monkeys were presented with a faint visual stimulus, a faint visual target stimulus of a duration of 200 milliseconds, either on the right side or on the left side of the screen. And in turn, the monkeys had to do a saccade to the target, and if they were right, they got a reward. So when the authors investigated what happens in the spontaneous activity before the target showed up, they found that this activity actually propagated in waves, and this is what we've seen before. So a microelectrode or microelectrode array implanted in the visual area MT. Next, they wanted to know if the more excitable state of these waves actually increases the spiking probability of the underlying tissue. And indeed, they found that the more excitable state of the wave increases the firing rate compared to the less excitable state. In the next question, they tried to address whether the spontaneous waves could modulate the response to the visual target. And indeed, they found if the spontaneous traveling waves aligned their more excitable state to the retinotopic location of the target arrival, then the neural response would be larger, significantly larger, as when the arrival of the target was locked to the less excitable state. And remarkable, they found when they investigated trials where they could not detect any waves, that this was not the case. So it seems that traveling waves specifically would modulate the response to this visual target and therefore gate perception. In another study by Rubino and authors, they found that traveling waves could mediate information transfer in the motor cortex. So they trained monkeys to detect, to basically reach for a visual target after a certain delay. And the monkeys saw 8 targets. One of them was visually cued, and after a certain delay, they had to reach for the cued target. So when the target was cued, they again found in the microelectrode array that waves would propagate. And you see this here in this time series. So the waves propagate from the upper left corner to the lower right corner. And not only did they find traveling waves propagating across this microelectrode array, but they also found that properties of the wave, such as the wave latency and the wave amplitude, actually contained information about the target direction. So in conclusion, Rubino and their colleagues suggest that these waves could actually transfer information intra and intercortically. In another study by Lyle Muller, in which I was also involved, we investigated sleep spindle oscillations, which are these 2 to 3 second oscillations of around 11 to 15 hertz that occur in non-REM stage 2 sleep. So if we look at sleep in humans, we usually cycle through a couple of sleep stages throughout the night. And this is indicated in this hypnogram down here. So typically we go from wake to N1, which is a transitory state, a very brief episode usually, and then we progress towards non-REM stage 2 sleep, which is where spindles occur, and they in fact characterize this sleep stage. And then we progress to deep sleep in non-REM stage 3. And at the end of each sleep cycle, we usually go through a phase of rapid eye movement sleep, and then we repeat this cycle. Now, sleep spindles have been shown to be crucial for memory consolidation, which is the process of transferring labile memories into the network of long-term memories of the cortex. And typically, memory processes are thought to be mediated by a process called spike timing dependent plasticity. And for those who have not heard about this mechanism yet, here's a little illustration. So you have a presynaptic and a postsynaptic neuron, and if their spike timing is aligned causally, meaning that the presynaptic neuron spikes before the postsynaptic neuron, then this could lead to long-term potentiation of the synapses. If they are acausal, meaning that the presynaptic neuron spikes before the postsynaptic neuron, then this could lead to synaptic depression. And these synaptic changes depend on the precise timing between those spikes. So the closer these spikes are to each other, the larger the changes, as you can see in the figure in the bottom. So in this study, we hypothesized that cortical traveling waves during sleep spindles might provide the perfect spatiotemporal framework for spike timing dependent plasticity to occur.